Problem 3 from our exam asked us to show that the equation x cubed plus x squared minus 1 equals 0 has a real number solution. So we're going to call upon a big theorem here, the Intermediate Value Theorem, and we're going to do a pure existence proof where I don't actually find what the answer is, but just explain why there has to be one. So first, it's really important to notice that in order to apply the Intermediate Value Theorem, it is important to notice that the function f of x equals x cubed plus x squared minus 1 is continuous. Right, but this is continuous. You can draw a graph here. Formally, it's fairly simple to prove that any polynomial is continuous. So this is definitely a continuous function, so the Intermediate Value Theorem will hold. Okay, next, note that, well, what is f of the value of negative 1? Well, f of negative 1 would be negative 1 cubed plus negative 1 squared minus 1. Negative 1 cubed is negative 1. Negative 1 squared is positive 1 minus 1. And negative 1 plus 1 is 0, minus 1 is negative 1. So we get that f of negative 1 is equal to, well, negative 1. Okay. Now let's stick in the value of 0. F of 0 is equal to 0 cubed plus 0 squared minus 1, which is equal to, is equal to negative 1 also. Well, that's not going to work because that wouldn't help our Intermediate Value Theorem catch a place where it's equal to 0. But let's do one more. That was my error, but it doesn't really matter for the proof. We'll be able to fix it up here. F of 1 is equal to 1 cubed plus 1 squared minus 1. 1 plus 1 is 2, minus 1 is 1, and that one's going to work for us. Because notice now that the outputs of the function from 0 to 1 go from negative 1 up to positive 1. In other words, it crosses the x-axis. So therefore we can say, by the Intermediate Value Theorem, the IVT, there must be a C between the two x values 0 and 1 such that when we evaluate the function f of c, we know that we get c cubed plus c squared minus 1, and we can say that this can be made equal to any number in between negative 1 and 1. So in particular we can make sure that we set it equal to 0 because 0 is between negative 1 and 1. So although I didn't find out what the exact solution was, what I've established here is that there exists a real number solution, which is what the problem was asking for.